Nope, it's just trash. Alright, so what the hell is it? Is it... Let's just disable the history writing and just use the history weight. And I'd like to finish up this stream by actually getting this data properly set up so you can have a good clean slate. God, I hate slate. So what does the yellow represent? The yellow represents... Well, let's see what it does. So we're taking our history, and our history is pushing stuff over to the side. It looks like we really need some sort of momentum in there. Like we need to really weight our direction here, because these guys got pushed backwards with their history, so we need to very much weight towards... Yeah, there's a lot of this where these things are just totally screwed up, so we need to... Why is the magnitude direction being handled separately? Because I didn't really find a very good way to join them into the exact same thing. Just basically normalizing and scaling vectors and stuff like that doesn't really work super well if they're all exactly the same. I don't know. I was going through a lot of stuff in my head, and it just wasn't making sense that the magnitude and the direction be completely tied together. Because magnitude is just, how fast things are going versus direction, which actually has not only magnitude tied to it, but, positive and negative and all that. And it's easier to get the magnitude, I think, correct. So it's more of an actual correct, I believe, thing, the magnitude. But the direction needs to be massaged into the right spot. So, should we do two things? Should we say, like, we want to head towards our initial position? Or do we want to head in the direction that we would have been going? There's a maximum history size of 10. We can just, like, super heavily weight it. It's like num equals 10. just like that. Like maximum history size. So if the history was in the complete wrong direction, how much do we want it to be influenced? I think maybe if every piece of history was in the wrong direction, we'll just multiply it by 1.5. Why don't we just do that? So if everything was in the wrong direction, we could slow ourselves down just a little bit, but not too much. Alright, so if we did that, we'd be okay. So what do we want to write in the actual pixel in the history? We want to write our direction, I think. We want to write our current direction into everything. So I should take this data right here and do this calculation here, and we should actually set our hist direction. We should just hist direction equals direction. So we'll try to weight our historical pixels in the direction that we're going, and just who cares? The history really, I guess the history we're not doing too much with. It's not too effective. We don't have enough pixels, and our simulation is not accurate enough to really do too much. Now, this is sometimes like a simpler simulation gives you a better answer than a more complex one. So what I'm kind of doing is like we've done all this work to like make all this gobbledygook crap, and I'm just like kind of cobbling it together to make it into something that looks halfway decent. And if we're like ignoring a whole bunch of information we actually have, that's not a problem. It's just we're just seeing what we can do with what we have. So let's see what this actually looks like. And we only had a couple particles simulated there. Just like that. So I need to actually tick this like a few times. So let's see what this looks like. And is that because of the histories are getting all sorts of screwed up? These things were just like hitting into the shore. These are going out. The history is taking them outside of the channel. It's because it's in the it's in the correct direction. So that's the direction that it's getting moved toward. We want to take it toward, like if this is going to bring it out, we want to bring it back in. Well, let's try not writing in the particle history, but weighting it more towards its initial direction. And the other thing we might want to do is maybe look at the path that we took. And we might want to calculate like how many steps we've taken, and like that's how far along the path we're supposed to have gone, so we could like kind of figure out another thing. Another direction, like the path is over there, we should go towards the path that we're supposed to be on. We need an actual tick here. Let's set it at 40. Alright, so 40 ticks. Generate the flow field. See what it looks like. It's close. You can see these objects. It's just the magnitude needs to be greater on the outside here, because these objects are doing what you would expect. They're kind of, there's a bunch of noise in here as these things fall off. Like these guys fall off here. They're gonna come down. Some of them go to the left. Some of them go to the right, and it's doing what it should. The issue is these guys aren't moving fast enough. The issue is our magnitude fall off is incorrect. Well, we might be able to try writing our magnitude in there just like that, and that might actually help us out. Because that's going to average out, giving us a bit more speed in there. Direction. So I'm trying to think what would solve this issue of these. This current is coming around here. It's just we're getting pushed out as we should, but we need to get pushed back in. We need a force that's going to move us back towards where we're supposed to be. Why don't I perform another search algorithm or something like that? That's not really... That shouldn't be necessary. Like, we know that's the path that we're supposed to be on, so... You know, it's not really... I don't see how it would help. And these guys are doing what they should. They're just kind of slowly moving over. We just need we need to take a path towards the curve and weight it in there. So we need to, if we get caught into this thing, get moving along. That path was made by me as a guide? No, it was not made by me. It was made programmatically. So I like how this is flowing in there. It's going to be these particles forcing, they tend towards moving stuff out. We need to move it out, but then we need to, if it's, the farther it is away from where it is, the more it needs to take it towards the line. We need to have a weight here back to not the starting position, but some other position in there. So we need a weight towards one of those. We need to take the number of ticks that we are at, and we need to figure out where in the line we are. So how are we going to do that? We need that information in this method, and we're going to have a weight that tells us to go in that direction. So the particle is going to need to know which which path it belongs to and which node it's on. So we're going to need the what? Tri-spawn. We're going to need to know which path we're on, and we're going to need to know which node we're on. So we need node index and path index saved on our flow path node. On our flow path particle. So this will be int32m path index and int32m source spawned node index. Alright, so we're going to need those sorts of things in here. So we'll throw them in. I gotta keep thinking about this. So this will allow us to move back towards our curve, basically. We can look up where on the path we're supposed to be at this point in time, this DT, and then we can go towards it. Alright, so we're gonna grab, this will be the grid index, so it's gonna be I, and then it's gonna be node index. So path index and spawned node. And we're not saving a pointer to it because other reasons. You're not always guaranteed that that memory won't get moved around or copied, and the stuff you're pointing to is now invalid. So I don't want to screw it up because it right now may be guaranteed that it won't move around. But then like I changed the order of some functions and everything goes to shit because I added one more particle onto an array, and all of a sudden all the index, the vector gets copied over somewhere else and we're blown to shit. Alright, so we're going to have path index equals this, and particle dot spawn node index is the other one. Alright. So we've now got that information that we need. So what we're going to want is, so if particle.m spawn node index is greater than or equal to 0, and particle.m path index is greater than or equal to 0, then we can apply some of these things. So what do we want? This is basically, we want the num to be I want this to be maybe 5 times as much. So we want to grab the node. So this is on the calculated flow field, so we're going to have impaths sub particle.path index. And so we're going to have int32 node index is going to be spawn node index and then the path goes this, so we'll do minus what particle that m ticks, so that'll go farther into the future. So if node index is less than 0, is greater than 0, greater than or equal to 0, then we're going to get a direction here. To path is going to be mpaths sub particle dot mpath index dot mpath sub node index, and let's actually get the node here in reference to it. So we'll have target node equals this. And why don't we have it be an exponential thing? So we're going to do like particle dot position history, not the position history, but the ticks multiplied by the ticks and all that. So to that will be what, target node dot mx minus particle dot mx and all that. And nodes have x's and y's, so we actually got to do the math here. It's not particle.mx, it's particle.mpos.x. And then target node.my minus particle.pos.y. And two path dot normalize two path. Let's put so we'll do in 32 two path weight equals particle dot in ticks times particle dot in ticks. So two path times equals two path weight. And then num plus equals to path weight and then direction plus equals to path. So we have an exponential return to the path. So we'll look up forward on the path and we'll go towards that based on something. So we're going to try to return to where we were. This probably won't work super well with S-curves and stuff like that that are large, but it should give us an idea. So as this particle lives longer, it's going to want to get back to where it should be on the path. And I could do a little bit more. I could actually do like a kind of a ray trace. I could kind of look over in the data and make sure there's actually a path to that target for every one of these particles, and just like discard this if it doesn't exist. Because I could go like step along this path and check if there are any shore tiles. But I don't know. I don't think it's probably not necessary. The shore repulsion stuff is supposed to handle that. Whoops. Well, this is also interesting. This right here, this picture is the actual A star for the Pathfinder, and it's actually not too awful in terms of what it's doing. I mean, that's just obviously super biased towards returning things to the middle of the river. So that's a little bit too strong. So let's lower the weight. Let's try not exponential. Let's just try linear. Oh man, yeah. One of the guys in chat is saying he got somebody on LinkedIn was messaging him about a job as a waiter, and he's like, somebody. I have a feeling somebody wrote an algorithm for finding jobs and put servers in there, um, and they're getting a bunch of tech people instead of waiters and waitresses. It's like I don't think that they got the right algorithm there. Wrong kind of server. Yeah, exactly. Man, it's really funny all the garbage on LinkedIn that you get. Like my friends and I have gotten so many messages with like the names aren't even filled out in the template fields. They're like, "Hello, like template name. How would you like to work at template company?" I'm just like, Jesus, really? It's like I'm not gonna respond to this message. Look at these guys are all sorts of screwed up. There's like some sort of black hole there. Where these the values of these objects intersect. Looks like the linear weight actually worked a little bit better. Um, let's just play with it a little bit and see what it does. It may be that a blur on there will get rid of those little black holes. But also, having a little bit of momentum on some of these objects would also have it, basically skip over what would be whirlpools and eddies and shit like that. And we're just like reading the texture, we're just reading the data directly, so it's not super amazing, valuable. So let's see if these guys actually make it over there. And the interesting thing about some of this is, there's no pathfinding over here. These particles are just dead reckoning to try to figure out where to go. So these guys over here where there is no pathfinder to figure out where to go is kind of what we want, is just kind of this stuff. See, that guy accelerates and then gets whooshed off over and off the cliff. It's actually really funny. It's like they're just lining up to die. It's like, it's a suicide roller coaster. It's like, yeah. So it looks like we're weighted a little bit too much towards. We want the initial direction to have more of an impact, I believe. This red is kind of pushing them out. So where's the red coming from? I think the red's going to be coming from these particles that get pushed away from here. Kind of the massing of them. Maybe it's that we don't have the hierarchical blur on there, so there's no good data in here. Maybe we should actually step forward. We should add, basically, this is where the particle is going to be, or should be. So maybe we could like add. So maybe we could do like minus like look ahead, and like in 32 look ahead equals like 5, or maybe we could look ahead maybe 10 pixels or more. Maybe we could look farther ahead, based on the number of ticks. We could do like 3 times the number of ticks is how far we look ahead. So we'd actually look farther ahead on the curve, and we try to go towards that. Let's just see. We're just kind of screwing around with this stuff to make it appear somewhat coherent. We could just keep messing with stuff. The next thing that we might want to do is actually just have like some sort of noise. Alright, we'll see how this goes. Just ticking more of this stuff. And what we want to see is we want to see some of this turn into kind of more yellow and green, I think, than this opposing. I want it more yellow, more green. Whoops. That should be an add, not a subtract. And as you can tell, I'm slowly just not being able to work anymore. Let's see. Been going for about this. I really want to finish up getting this into a decent state. Doesn't need to be perfect. It just needs to be closer than what we've got right now. But it is actually pretty close. Like, they're doing what they should. There's just, you know, maybe some averaging out here will pull this in and make it work properly. So we'll see. That's looking like it might have averaged out a little bit. These guys are climbing over the fucking... Alright, the look ahead is too strong. Shit. That's gonna be what I was talking about with, like, the look ahead needs to not work nearly as much. So maybe we need to write the avoidance vectors after we write everything else. That would be the other thing to do. So what do these guys do? They do the right thing? Yeah, see, now they're actually doing the right thing where you'd expect them to kind of go forward. So I do like that. I just don't like all of that. So why don't we change the order so we write the shore edge maybe afterwards? And what is... Yeah, let's just try it. Let's just look at what it would actually do. Because I think my initial calculations were that I would have a weight in there and I'd weight everything and then do like some stuff on it, but that hasn't really panned out. It didn't really make much sense to me coming in. Maybe I was wrong to not do that together, but when I was when I was just thinking about it, it was like there's too many weird things that are gonna come in and screw this up. Too many issues where it'd be like, well, if I add too many things in here and then have like a total number of ads and divide it at the end, maybe data's gonna get lost. There's only so much space inside of a floating point value for you to do incremental stuff with it before it blows up in your face. So we'll take it, so we'll have our particle sim, and we're going to apply our shore stuff after everything. We'll see how it actually looks. So sharing our flow field, we're going to see a much larger shore radius influence on this. So let's take a look at what it actually looks like now then. The look ahead is just too powerful. It's just too damn powerful. So let's see if these guys actually will make it over there at all. They're paddling, they're trying their best to get over there. Yeah, that's why I picked this animation, because it looked like they're just flailing miserably. So it's looking proper, except for over here where these things are sticking so close to the shore. It's just absolutely insane. And that's definitely the shore edge detection crap. So let's just remove the look ahead and see if see what that does. Look ahead of 0. I'll just start messing with stuff and seeing how it looks, and we'll try to massage it into kind of a compromise. I'm okay. I'm totally fine with the thing where it moved back a little bit, but then joined the path. Like that's fine. I'm not okay with all this like crap jumping at a shore so hardcore. Needs to not do that. Alright, so let's see what this does. So those guys hit and they're kind of flailing around. They're going on their little path. They're doing their thing. Alright. And the other thing is, you have to realize that these guys are going to be following the same rules that the water under it is going to be drawn with. So if they're going the wrong way and then going the right way, the water on the surface of this thing is going to be doing that. It's going to be all roiled and messed up. So even if it's inaccurate, your brain will fix it with whatever geometry should be on the bottom of the lake or whatever the hell this thing is. You'll be like, oh yeah, there's like something there that's causing all this weird crap to happen. So I'm not really too incredibly worried with a lot of it. So I'm okay with this. So let's get our averages working. This is what I'm thinking.